In this video, we're going to talk about the concepts of covariance, correlation, and what the concept of statistical independence means. We've mentioned statistical independence before, but we can now think about it in terms of joint probability density functions. Two random variables are statistically independent if the distribution of each variable is unaffected by the level of the other variable. That implies that if two random variables are independent, the conditional probability density function will be exactly the same as a marginal probability density function. So the conditional probability of observing x given y is just the marginal probability of observing x, and it doesn't vary with the level of y. And similarly, the conditional distribution of y with respect to x is just the marginal probability of observing y, and that doesn't vary with the level of x. And in that case, the joint probability of observing x and y is just equal to the product of the marginal probabilities of observing x and y. Since we're dealing with the relationship between two variables, we can now define the concept of covariance. The covariance between x and y is the expected value of the product of the deviation of x from its mean and y from its mean. In the case of discrete distributions, we're taking the sum of the product of x minus mu sub x and y minus mu sub y over all possible combinations of x and y, and we multiply each of those by the probability of observing that combination of x and y. A positive covariance is said to occur when x and y tend to vary in the same direction, when there's a general upward sloping linear relationship, as on the diagram on the left. A negative covariance is said to occur when we have a general inverse relationship between x and y, as occurs in the diagram on the right. The points that are illustrated here are simulations from two sets of data, one where there's a positive covariance and one where there's a negative covariance. What we observe is that when we draw in mu sub x and mu sub y, if we look on the new set of axes contained in the xy coordinate system there, in the top right portion of that diagram, x is above its mean and y is above its mean. So the product of points in that area will be positive because positive numbers multiplying other positive numbers are positive. If we look at the bottom left portion of that same diagram, there x is below its mean and y is below its mean, and as a result, we end up with a negative number multiplying a negative number, which also gives us a positive product. Now, in the upper left and the bottom right, we're multiplying a negative and a positive number. But if most points fall in the top right portion of the diagram and the bottom left, the expected value of that, when we weight each outcome by the probability of observing it, will tend to have more weight placed in the top right and the bottom left quadrants, which results in an average value that's going to be positive, which is why we call it a positive covariance. In the diagram on the right, we get something different. Most of the observed data points, most of the density of the distribution falls in the top left and the bottom right portions of the diagram. And in those regions, the products of the deviation of x from its mean and y from its mean would both be negative, and therefore would observe a negative covariance. If x and y are independent random variables, the covariance between x and y will always be zero. There's no relationship in that case between the variables. However, a covariance between x and y of zero does not necessarily imply statistical independence. This diagram on the right can illustrate that. Here we observe there's a very strong relationship between x and y, but for every point on the left top or the left bottom portion of the diagram, there's some point with equal weight on the right portion of that with the opposite sign. When we look at the average of all these outcomes weighted by their probabilities, we'd end up with zero, even though there's a very strong relationship between x and y. Covariance is a measure of the degree of linear association. It's not a measure of independence. If you have a nonlinear relationship between x and y, you might very well end up with a covariance of zero, even if the level of x helps explain y and vice versa. So if you find a covariance of 0, that can tell you that there appears to be no linear relationship, but a covariance of 0 does not tell us that the variables are unrelated or that there's statistical independence. If we're looking at the covariance between GDP and consumption spending, we get dramatically different measures of covariance depending on whether we're measuring these variables in billions or trillions of dollars. So what we tend to do is we work with a correlation coefficient. And the correlation coefficient is defined to be the covariance between x and y divided by the standard deviation of x times the standard deviation of y. The value of this is bound between +1 and -1. You can find a proof of that in most college-level statistics textbooks. By dividing through by the standard deviations, we come up with a measure of covariance which is independent of the units of measurement. If we find a correlation coefficient of 1, that means all the points would fall with 100% probability on an upward sloping line. A correlation coefficient of -1 would tell you that all the points fit exactly on a negative sloping line. A correlation coefficient of 0 would say there's no relationship. A correlation coefficient of 1/2 would tell you that variation in x is explaining half of the variation in y. And we'll talk about that in more detail later. There's a couple of other properties that we can talk about with variances now when we deal with multiple variables. We should talk a little bit more about some properties of the variances of these variables. If x and y are two random variables, the variance of the sum of the variables equals the variance of x plus the variance of y plus twice the covariance between x and y. If x and y are two random variables, the variance of the difference between x and y is again the sum of the variances but minus twice the covariance. If x and y are independent, though, the sum or difference of x and y just becomes the variance of x plus the variance of y, because remember, when variables are independent, the covariance will always be 0. The last property is that if x1 through xn are independent random variables and a1 through an are constants, then the variance of this weighted sum of random variables is just the sum of those squared constants times the variance of the x's.